Now that we have some intuition for Newton's method, let's derive it. So you remember that we said that the basic idea, is to make a second order approximation, and minimize that. So this is going to be our guiding principle. So let's take some function f. So let f be a function from, say, r, well, let's make it rn to r. It's some real valued function. And let's just say that it's sufficiently smooth for our purposes. You know, that it has enough continuous derivatives to do whatever we need it to do. Then, to make a second order approximation, the thing that we always do when we make a polynomial approximation to a function is we use Taylor's theorem. So Taylor's theorem tells us that f can be approximated. So if we have some point A, and then we want to look at points x which are near A, then f of x is approximately f of A plus the gradient. Let me just write g for the gradient. The dot product of the gradient with x minus A plus 1/2 x minus A transpose. So this is Newton in multiple dimensions times the Hessian times x minus A. So this is the second order approximation, and here g is the gradient of f evaluated at A, and h is the Hessian, which is the matrix of second derivatives. So sometimes we write this, and it's all the, put it here, all the second derivatives, partial with respect to xi and xj for I and j going from 1. So it's that evaluated at A for I and j going from 1 to n. So that's Taylor's theorem, and this is for, you know, for x near A. And let's simplify this down a bit. All we just want to get this to look like some nice second order function. So let's simplify it. Let's actually also switch colors. Let's pull together some stuff and just rename things to make it look like a nice second order thing that we can minimize very easily. So if we multiply this out, we get x transpose hx times 1/2. And then let's pull together the linear parts. So we're going to get g transpose times x, and then, well, let's just call it something. Let's call it b transpose x, and then we're going to have c. And here b will be, we'll just define b appropriately. What's b going to be? B is going to be g minus, and then what are the linear parts over here? Maybe I should multiply this out to see what it's going to be. Let's multiply this out. Keep the same color. This is x transpose hx minus 2 a transpose hx plus a transpose ha. So the linear part is this minus 2a transpose h, so we transpose that, and we're going to get ha. H is always symmetric. The Hessian is always symmetric. And we get a minus there. The 2 cancels. And so this is going to be g minus ha. So that will be our b for b. And then c is going to be whatever else, you know, whatever's left over. I guess let's make it precise. So it's going to be f of a minus Well, we don't need to make it precise. C is just whatever's left over. It's not really particularly important. I don't think it's going to be important, at least. Okay, so we expressed it in this form, and now we want to minimize this. So this is our approximation. Let's call this Q. So quadratic approximation of f. And let's minimize this. So to minimize this, we just do the usual thing. Take the gradient. We get hx plus b. And now, right, we set that equal to 0. So now we should solve for x to find the point which is the minimum. And that's going to be minus h inverse b. And let's plug in b here to figure out what this is in terms of sort of the original stuff, g and a. So let's plug this in. We're going to get, what are we going to get? We're going to get minus h inverse g plus a. So that's a minus h inverse g. And the Hessian, it might not necessarily be invertible. So this can break down if the Hessian turns out to not be invertible, and you'll have to do something else. So that's one sort of caveat here. Okay, so this gives us our minimum, right? That was what we wanted. We made our second order approximation, and then we minimized it. So we got the new x. So this tells us, well, I guess first we should check to make sure that it's a minimum. So let's do that. So to make sure that, so that's a critical point. We know that if x equals, let's go ahead and write what we got here. X equals, well, so if x equals this, then we know it's a critical point. And to check that it's a minimum, we need to see that it's at least positive semi-definite. And to do that, we need to take the second derivatives. So when we take the second derivative, when we differentiate this again, we just get h. We just get the Hessian. You can check these vector calculus steps if you like. These are some nice shortcuts that you can use to more easily derive these formulas. So the second derivative, the Hessian of Q is also the Hessian of F. So that's great. And well, it's nice at least. But the nice thing is that as long as F is a convex function, or at least as long as it's convex at this point A, then the Hessian of Q is also, so if F is convex, then its Hessian is positive semi-definite, and so the Hessian of Q is positive semi-definite, and that would mean it's a minimum. So this implies minimum if H is positive semi-definite. And so we get our algorithm. You know, just like before in the 1D case that we mentioned, there are some caveats that this can break down. It might not necessarily be giving you a minimum, but the algorithm is, you know, as long as everything is going well, what you do is the following. Algorithm. If I can spell. Algorithm. So first, you initialize x0. Maybe choose it to be 0 or something like that. You might have some smart way to initialize it. And then iterate on the following expression. Xt plus 1 equals xt. So it's going to be this thing. So if xt was our a, right? So we were deriving this. We were expanding about this point a. So that was our old point. And we were minimizing it, and our new point, our xt plus 1, was this x. Right? So xt plus 1 should be equal to xt minus h inverse times g, where h is the Hessian, or maybe I'll just put g first. G is the gradient of f at xt, and h is the Hessian at xt. So that's it. That's Newton's method for optimization. And let me mention a couple issues that can arise here and how to address them. So possible issues. Let's do it in a nicer color. Issues. Possible issues. One is that, as we sort of found here, or as we noted, h may fail to be positive semi-definite, or maybe fail to be positive definite. If it's positive definite, then everything is great, because then we know that we're minimizing, we're going in the right direction. We're minimizing that q, that our quadratic approximation. But if, and so that's the sort of case that we were back up here to our examples. That's this sort of case here, as opposed to this sort of case. Because if it's not positive definite, well, it may be only positive semi-definite. It might not be invertible, and then you can't you might not be able to do this. Certainly might not be able to invert h. Would not be able to invert h. But what you can do in this case is either, so the typical thing, or one thing that people do, is switch to gradient descent in this case, if it's not positive definite. And that's called, so the Levenberg-Marquardt algorithm is a smart way to switch back and forth between those two algorithms. Okay, so that's one issue. Another issue is that, and this is actually something that you might always want to do, is you may want, rather than invert h directly, you can solve the equation hy equals g for y. And you can do this more, sometimes you can solve this, there are algorithms for solving this more quickly and more numerically, using more numerically stable methods than by inverting h directly. And so if you can solve this for y, so that was sort of, so you would solve this for y, and then use xt plus 1 equals xt minus y. So mathematically speaking, these are equivalent. This and this original formulation are equivalent, but for computational reasons, numerical and computational efficiency reasons, this is a more robust approach. And one last thing to mention here is that oftentimes people modify this to use xt plus 1 to be xt minus some rate parameter alpha t times h inverse, or times y, I guess, in both cases. And the reason for this is because, so you would choose alpha t to be some, say, small positive number, and you can control, so this is like your step size. So this gives you more control over the rate that it's converging at. So that's Newton's method for optimization.